Hello students, Chegu here, and today we're going to make sure you absolutely master the chapter on heat. Now whether this is your first time looking at it, or you're just here for a quick revision, don't worry, I've got you covered. Okay, let's dive right in.
First up, let's get this sorted once and for all. It's the question that confuses almost everyone. Are heat and temperature the same thing? Well, the answer is a big, definite no. And you know what? Understanding why they're different is pretty much the secret to acing this entire chapter.
So, Section 1. What is heat, really? Let's build a strong foundation by looking at energy, temperature, and something called equilibrium.
Okay, look at this table. It breaks it down so nicely. Heat is a form of energy, specifically the total energy of all the particles in an object. We measure it in joules. Temperature, on the other hand, isn't about the total energy, it's about the average energy. It's a measure of how hot something is, or how fast its particles are moving. So get this, a huge swimming pool of warm water actually has way more heat energy than a tiny cup of boiling water, even though the cup's temperature is much, much higher. Makes sense, right?
And this leads us to a really key idea: thermal equilibrium. You see, heat is always on the move, flowing from a hotter object to a colder one. It's a one-way street. And when does it stop? It stops when both objects reach the exact same temperature. Think about it. You make a hot cup of Milo, then you pour in some cold milk. The heat from the Milo flows into the milk, warming it up until everything is just one nice warm temperature. That balance, that's equilibrium.
All right, on to Section 2. How does heat actually move around? Think of it like this. There are three main highways that heat energy uses to travel.
Remember these three names, class: conduction, convection, and radiation. I can almost guarantee you will see them in your exams. So let's break them down one by one so you understand them perfectly.
First up, conduction. This is basically heat transfer by touch, and it usually happens in solids. Imagine you're all sitting in a line, and you whisper a secret to the person next to you, who then whispers it to the next person, and so on. The secret message travels down the line, but nobody actually gets up and moves, right? That's conduction. The particles just vibrate and pass the energy to their neighbors. It's why metal spoon gets hot when you leave it in your tea.
Next is convection, and this happens in liquids and gases, what we call fluids. Here, the particles themselves actually move. When you heat a fluid, say water in a kettle, the water at the bottom gets hot, it expands, becomes less dense or lighter, and it rises up. Then the cooler, denser water from the top sinks down to take its place, gets heated, and rises up too. This creates a cycle, a circular flow, called a convection current.
And a perfect real-world example of convection is a sea breeze. During the day, the land heats up way faster than the sea. So the air above the land gets hot and rises. This creates a low-pressure area. And guess what? The cooler, denser air from over the sea rushes in to fill that space. That's your nice, cool sea breeze. This is a very, very popular exam question, so please take note.
And the third one is radiation. So how does the heat from the sun get to us? It's millions of kilometers away, across the empty vacuum of space. There are no particles to conduct or convect. Well, the answer is radiation. Heat travels as electromagnetic waves, just like light. It doesn't need any medium to travel through, and it's the fastest way for heat to get from one place to another.
Okay, Section 3. Let's talk about the big effects of heat. What actually happens to stuff when it heats up or cools down?
Here's the golden rule. You have to remember this. Heat makes things expand, and cooling makes them contract. Simple, but why? Well, when you heat something, you're giving its particles more energy. They start to vibrate and move around faster and push each other further apart, so the whole object gets bigger. And when it cools down, the opposite happens. The particles lose energy, slow down, get closer together, and the object shrinks.
And this is so important in the real world. Engineers have to think about this all the time. You know those small gaps you see in railway tracks? They're there on purpose, so when the tracks get super hot under the Malaysian sun and expand, they have space to grow without bending and buckling. Same reason bridges have rollers and power lines are hung with a bit of a sag. It's just physics in action. Okay, time for a fun little trick. Let's say you're playing ping pong and you accidentally dent the ball. Oh no! But wait, how could you use what we just learned about expansion to fix it? Any ideas?
The answer is, just put it in some hot water. It's so simple. The air trapped inside the ping pong ball gets heated by the water, the air particles get more energy, move faster, and expand, pushing the dent out from the inside. Pop! Good as new. This is a perfect example of gas expansion and a great little tip to remember for those practical application questions in your exam.
Moving on to Section 4. Let's talk about surfaces. Dark versus shiny. This one is super important and explains a lot of things we see in everyday life.
So here's the deal, and it's actually quite straightforward. Dark and dull surfaces are great at absorbing heat. But here's the other side of the coin. They're also great at radiating or emitting heat. They're good at both taking it in and giving it out. Now, white and shiny surfaces are the complete opposite. They are poor absorbers because they reflect most of the heat. And they are also poor radiators. Just remember that simple rule.
And this chart shows it perfectly. If you took a black can and a white can and left them out in the sun, you'd see the temperature inside the black can shoot up much faster. Why? Because its dark surface is absorbing much more of the sun's radiation. The white can, being a good reflector, stays much cooler.
All right, class, we're in the final section. Let's do some quick-fire revision. These are classic exam-style questions, so try to apply everything you've just learned. Are you ready?
Okay, first question. You see those huge fuel tankers on the highway, right? Why are they almost always painted a shiny silver color? Think about what we just learned about shiny surfaces. What's the main goal for a truck carrying flammable fuel on a really hot day?
Exactly. The shiny surface is a poor absorber of heat. It acts like a mirror, reflecting the sun's heat radiation away from the tanker. This is a critical safety feature to keep the fuel inside cool and reduce the risk of it evaporating or becoming dangerous. Okay, next one. And this is a very serious safety warning, not just for exams, but for real life. Why should you never, ever throw an aerosol can into a fire? Think about the gas trapped inside and what happens when it gets very, very hot.
That's right. The intense heat gives the gas particles inside a huge amount of energy. They expand rapidly inside the sealed metal can, and the pressure builds up and up and up and up until the can can't take it anymore and it explodes. It's extremely dangerous, so please always remember that.
And for your final challenge, I want you to think like an engineer. Using everything we've talked about today, how would you design the perfect tiffin carrier to keep your lunch nice and warm for hours? You'd have to stop conduction, convection, and radiation. What materials would you use? What kind of surfaces, inside and out? That's your homework. Thanks for joining this explainer. Study smart, and I'll see you in the next one. Good luck!